Hi, I'm Sierra. I'm a physics undergrad at Michigan State University. On screen, you're going to see some problems from Chapter 4 of Thermal Physics by Kittel and Kroemer. Why don't you go ahead, pause this video, read through those problems, and then the rest of the video is going to be me working out the solutions to those problems. Hope you enjoy. Okay, the first part of our problem asks us to show that the total energy generation rate for the sun is 4 times 10 to the 26th joules per second. Okay, so, and we're given the solar constant of the Earth. We want to consider that we have a sun some distance from the Earth, and we on Earth get a flux from the sun, right? That's equal to our solar constant. But the sun is going to radiate this flux isotropically in all directions. So to get the total from the sun, we want to take our solar constant and then multiply that by all of the directions that it can go. So it would be 4 pi times this radius, right, from the sun to the Earth squared. So 4 pi r s sun to Earth squared. Yeah. Okay, and if we multiply these out, we just get 4 times 10 to the 26th joules per second. That was really easy and painless. Okay, what happens if we take this and we divide it by the surface area of our sun? 4 pi times our radius of our sun, given here by 7 times 10 to the 10th centimeters squared. Okay, well, this gives us an energy flux density. And in part B, we're asked to show the effective temperature at the surface of the sun. Okay, this energy flux density, we use Boltzmann's law to relate this to temperature. So we have an energy flux density, we know Boltzmann's constant, we can figure out temperature by setting this value equal to Boltzmann's constant. Okay, so then we get that T to the 4th equals 4 times 10 to the 26th joules per second divided by 4 pi 7 times 10 to the 10th centimeters squared. Boltzmann's constant is up there, 5.67 times 10 to the negative 12 joules per second centimeters squared, Kelvin per 4. And if we multiply this out, we'll get around 6,000 Kelvin. And we can find the surface temperature of our sun. Okay, the next thing we want to do is estimate the order of magnitude of the gravitational self-energy of the sun. So we'll start this out by writing the differential for this potential. Hopefully something of this form looks familiar to you. And we're going to go ahead and write this in terms of variables that are more useful to us. So we'll consider a density, rho. So we have our mass, and volume isn't super helpful, but we can rewrite this in terms of the radius, 4/3 pi r cubed, which is something that we have. And then we can write our mass as 4/3 pi r cubed rho by just solving for m from here. From here we can get the differential element dm. So it's going to be 4 pi r squared rho dr. All right, by chain rule. Now we can substitute those in to our original du expression. So du is negative g 4/3 pi r cubed rho 4 pi r squared rho dr over r. We integrate both sides. We're going to integrate this from 0 to r to get an expression for u. This expression for u is going to yield negative 15 over 16 g pi squared rho squared r to the 5th. We're going to substitute in for rho squared. negative 15 over 16 g pi squared. Rho is m over 4/3 pi r cubed squared r to the 5th, which is going to give us negative 3/5 g m squared over r. Now, if we plug in our mass of the sun, radius of the sun, and gravitational constant from up there, we yield negative 2.26 times 10 to the 41 joules. The next thing we want to do is estimate the thermal energy in the interior of the sun, which is kind of crazy that we can predict that. Anyways, so it tells us to do this using the Virial theorem, which states to assume that our thermal energy is going to be negative 1/2 times our potential energy, which we calculated earlier. So it's going to be negative 1/2 times negative 2.26 times 10 to the 41 joules. Okay, now what else can we relate this to? How do we relate this to temperature? Well, what else is our thermal average energy? It's going to be our number of particles times the average energy of each particle. Makes sense? Okay, but what's our average energy of each particle, and how does that relate to temperature? So if we use the equipartition theorem and we assume ideal gas form, we have 3 degrees of freedom, which each contribute 1/2 in x, y, and z. So we have a factor of 3/2, and we do our Boltzmann constant times temperature. That gives us the average energy of each particle, and again, we're still multiplying by the number of particles. Now, we can set these two things equal to each other. Negative 1/2 or 2.26 times 10 to the 41 joules. And we have our n, our number of particles is given as 10 to the 57. So 10 to the 57 times 3/2 kBT. We can plug in 1.38 times 10 to the negative 23 with units for kb, and we can solve for t. I'm not going to do all that. I'm just going to give you what t is. This comes out to be about 5.46 times 10 to the 6th Kelvin. Just as a check, this should be larger than what we got for the surface of the sun, and it's definitely larger. And again, our book states that this result is going to be a lot lower than it should be, because we're not taking into account that the density of the sun is not uniform. But we can serve this as a first pass, right? Hotter on the inside than on the surface. Cool. Okay, first thing we want to do is find the total energy of the sun that is available for radiation, assuming our energy source comes from this fusion reaction. And to start doing this, we want to use the Einstein relation, E equals mc squared. This is but you've never heard of this one before. Okay, but what's our delta M for this fusion reaction? Well, this is going to be 4 times our mass of hydrogen minus our mass of helium. And I give these to you over here. So 4 times 1.0078 AMU minus 4.0026 AMU. This is going to come out to be 0.0286 AMU. And then we use this to solve for E, 0.0286 AMU. We want to convert this to SI units. We know that 1 AMU is equal to 1.66 times 10 to the negative 27 kilograms. And then our speed of light squared, 3 times 10 to the 8th meters per second squared. Come out to be 4.27 times 10 to the negative 12 joules. Okay, now we know the energy of one fusion reaction, but to find the total energy of the sun that is available for radiation, we need to figure out how many times this happens. Okay, so let's consider the mass of the sun and the fact that this reaction stops when 10% of hydrogen is converted to helium. So you take our mass of the sun times 10%. Our mass of the sun is given to us as 2 times 10 to the 33 grams. We're going to convert this to kilograms, multiply by 0.1 to give us 2 times 10 to the 29 kilograms. Okay. Now, to calculate the number of times this happens, we want to consider this mass, 2 times 10 to the 29 kilograms. And we want to consider how many protons are in this mass. And we can do this by using the fact that 1 AMU is 1.66 times 10 to the negative 27 kilograms, right? So total kilograms divided by the weight of a proton is going to give us how many protons? Okay, but each reaction is going to take 4 of them. So we want to divide this by 4 if we want to figure out how many times this reaction takes place. Okay, cool. 3.01 times 10 to the 55. Now, to get our E total, we take the number of times this happens, 3.01 times 10 to the 55. We multiply that by the energy of the fusion reaction, which we found earlier, 4.27 times 10 to the negative 12 joules. 1.28 times 10 to the 44 joules. Okay, now we have a value for total energy, and we're also told the rate at which the sun radiates energy. And from this, we can find the lifetime by simply dividing these two. Now, this is going to come out in seconds, which is a pretty non-intuitive way to go about things. So if we do some dimensional analysis, we get 1 hour is 3,600 seconds times 24 hours is 1 day, and 365 days in 1 year. This will give us our lifetime in years, and this is going to come out to be about 10 to the 10 years, or 10 billion years, which is a long time. All right, so that's it.